Alrighty, so time for the read and got it. If you don't have the vocab memorized, it might be a good idea to go back and do that. So make sure you've done the vocab at least so that you know what I'm talking about. So anyway, starting out here, it's solving a system of equations. Again, a system of equations has two or more linear equations, or two more equations in this case. And currently we're going to use the graphing method to solve them. So, it's our benefit that they come out nice, right? And you're going to want to graph them as absolutely perfectly as you can to find the solution. So graph y equals x plus 2, looking like this, right? So here's the 2, right, the y-intercept, and the slope is 1. So up 1 over 1, up 1 over 1, bam, keep going. And graphing 3x minus 2, so y-intercept of negative 2 down here. And slope of up 3 over 1, up 3 over 1. And we find out those two run into each other at exactly the point 24. So that's the idea we're doing right now. This is the easy part of this. Well, I don't know. The algebra part's not terrible, but I think it's better. But all right, so there you go. So we're going to graph these two, and luckily for us, they're already in slope-intercept form. So we're going to need to figure out where the y-intercept is. So the first one, this top one, y-intercept at plus 4. So let's see here, I need my marker. 1, 2, 3, 4, right there. And a slope of 2. So up 2 over 1. And we can go back if you prefer. And hang on, let me grab a ruler and we'll draw that line. Struggled a bit making that happen. Alrighty, so anyway, next up we're going to graph x plus 2. I'm going to switch to blue for that. And so my y-intercept is right here at 2. And the slope is down 1 over 1, or up 1 over 1, however you prefer to look at it. And, you can already see the point right there that they're going to go ahead and intersect. So let's go ahead and graph that one real quick. There we go. And we can see that they intersect right here at negative 2, 0. That's really all there is to it. So graph them, find where they intersect. Graph carefully, folks, especially on these, because they're going to come out nice. I'm not going to even something comes out at like negative 2.75, 3.29. That's crazy. I'll do that on other ones, but not this type. You guessed it, we get to do story problems too. I know you're excited. So here we're going to write a system of equations for this. Biology, not my favorite class. Scientists studied the weights of 2 alligators over a period of 12 months. The initial weight and growth rate of each alligator are shown below. After how many months did the alligators weigh the same amount? Okay, so initial weight, that's going to be like the getting in the taxi fee or the cheese pizza fee, right? Growth rate, that's going to be the slope. So a lot of these are going to be like this, easy enough to write. So this one starts out at 4 pounds, right? So 4 pounds down here. And a growth rate of 1.5 per month. So guess what? Slope 1.5 times t time in months. Alligator 2 started out born at 6 pounds. Apparently he's a little bigger. And a growth rate of 1 pound a month. So slope of 1 times t months. So again, we get W equals, so that's the weight at any given time. W plus 4 plus 1.5 t. 6 plus t, or 1t if you prefer. Now, obviously, it doesn't make any sense to go back in time because that doesn't work. And we graph those two lines, find out they intersect at 410. So just like the others, but you get to write your own equation. So you can pay attention to those things, like that cheese pizza fee, right, or the get in the cab fee, the initial amount there, and then times the slope. That's always going to be called a rate of some kind. Alrighty, so here we have, I'm going to get a finer point here. Here we have this one satellite radio service charges $10 per month plus an activation fee of $20. So a second service charges, so we're going to say service 1, right? A second service charges $11 per month plus an activation fee of $15. What month will they cost the same? Alrighty, so we're going to say, don't forget this here, let M equal number of months. Okay? And that's going to be our input variable along here, right? That's going to be our X is going to be months. And Y axis is going to be cost. Okay, look familiar? Alrighty, so that first one, they charge, so we're going to say Y, or C cost if you prefer, right? So C, let M, I put it right up here, there we go. C cost equals, let's see, so we're going to have plus $10 per month plus the $20 activation fee. The other one charges $11 a month, so C equals $11 per month plus, no, that's not a very good plus, plus a $15 activation fee. So they're really similar. So we have to do is graph those two and figure out where they intersect. So I'll do this one in red, right? So we have, oh, that's going to be a little tougher to pull off, isn't it? It's 10 and 20 here. I don't actually have a 20, do I? So let's see. We're going to have to count these. Give me a second here. Yeah, I'm going to tell you right now, this isn't fitting on here. So I just went, I grabbed a piece of graph paper and thought, oh, let's do it on there. And I don't know what person wrote this. It's a great problem, but not one for graphing, because your solution is at 5 months and the cost is at $70. That's not fitting on here. That's not fitting on a piece of graph paper. Now, if I had all of these were like, tens, but there's not. There's an 11 here. If I had all these were tens, it'd be, I'd go, oh, let's go by fives, let's go by whatever. But because this is 11, it makes it a little tougher to try to do that and come out exact. So I'll just tell you right now, this one is after 5 months and at $70 that these two are equal. A way easier way to solve this one would we going to learn later on. You would basically set these two equal to each other, and then just solve for m. I mean, it's not really a big deal, but this is a terrible problem for graphing. So anyway, do apologize for that. 570 is where they intersect. So 5 months. Okay, so now we have to talk about systems with infinitely many solutions or no solutions. Again, that's part of your vocab. So we take a look here. Now, this one's kind of fun because hopefully you catch on quick enough. The two lines are the exact same line. So I have these two right here, and I go to graph them. And I find that, well, if I translate this one into slope-intercept form, guess what I get? This line, which is why it's nice to be able to translate into the same form. I recommend that. Turn them into the same form, whether it be slope-intercept, standard form, whatever you like the best. If you see they're the same, boom, I can graph it. That's great and all, but they are the same line. So, again, infinitely many solutions. Likewise, once you put them in slope-intercept form, and you find they have the same slope, notice these have the same slope, 2x, and different y-intercepts, you know that they're parallel lines. That's something we learned before break. Same slope, different y-intercept makes them parallel, and if they're parallel, they have no solutions. A couple of examples for you. So we'll draw the first one, this one right here in red, and so y equals the opposite, or negative x, or the opposite of x minus 3, so that starts out down here, and the slope is -1, so it's going to go like this, right? Going to go like this. Oh, you know what? No, that's not what it's going to go like. Hang on, sorry about that. I said negative slope, so start it again, right? -3. Negative slope, that's better. See? Watch out for those mistakes there, folks. And then we also have, I'll graph this one in blue, and I need to, I guess, finish in the line for this one. So we'll draw that in. Looks like this. There we go. Now the other one, we have +5. So 1, 2, 3, 4, 5, and the same slope. And as we said before, same slope, different y-intercept, then they are clearly going to be parallel lines. And we can see that with these two, that they're never going to intersect. They have the exact same slope. Going to make parallel lines. So no solution for the first, got it there. Alrighty, so here, let's see here. So the first one is I'm going to graph that in red. So y-intercept -3, and slope of 3, going to go like this. And that's the nice thing with these, for the graphing ones. I'm always going to be kind of nice to you and make them easier to graph, and they'll be easy to find the intersections between the two. And the other one, well, that one's a little bit tougher, but you notice I have a 3 in common among all these, so I can literally divide that out. So that becomes y equals 3x. Oh, -3. Look at that, same line. So down here, and so on and so forth. So these guys are going to have infinitely many solutions because they're the same line. Okay, and the last of those Before graphing the equations, how can you determine whether a system of equations has exactly one solution, infinitely many solutions, or no solutions? So I'm going to tell you first off what I would do. Put them in the same format. Slope-intercept, because you can see the slope and the intercepts immediately. You can tell if they're parallel because they have the same slope but different intercepts. Tell if they're the same line because they have the same slope, same intercept, like literally the same line. You can tell if they're going to have one solution because they don't have matching slopes, and then the intercept, if the slope doesn't match, the intercept itself doesn't match. So they're going to, it doesn't matter rather, so they'll have exactly one solution.